Right now, more than 15 billion miles from where you are sitting, a spacecraft the size of a small car is hurtling through absolute darkness at 38,000 miles per hour. It has no destination, no brakes, no way to turn around. Voyager 1 is the farthest human-made object in existence, and it is still talking to us, but not for much longer. Every year, its nuclear heart loses a little more power. Every year, another instrument goes dark. Engineers on Earth are making choices right now about which of its last remaining sensors to shut off and which to keep alive for one more year. There will come a moment, and it is closer than most people realize, when the farthest thing humanity has ever built stops answering. If this is the kind of deep space story that pulls you in, hit like and subscribe. We cover the missions that actually push the edge of what humans have done out there. Are you comfortable? Now, let's begin. There is a number that most people know, but very few people feel. 172 astronomical units. That is how far Voyager 1 is from Earth right now. It is the farthest human-made object in existence, farther than anything our species has ever thrown into the dark. If you opened a browser and searched for that distance in miles, you would get a figure somewhere north of 15.5 billion. In kilometers, it crosses 25 billion. Those numbers are real. They are accurate, and they are almost completely useless for understanding what they actually mean. Here is a better way to think about it. Light is the fastest thing in the known universe. Nothing in physics moves faster. A beam of light leaving Earth right now, traveling at 670 million miles per hour, would need more than 23 hours to reach Voyager 1. Not 23 minutes, 23 hours, almost a full day just for light itself to close the gap. If you sent Voyager 1 a message this morning, a single command, a question, a greeting, and if everything worked perfectly, you would not hear back until the day after tomorrow. That is not a delay caused by slow technology. That is a delay imposed by the structure of the universe itself. Voyager 1 is so far away that it takes the fastest thing in existence an entire rotation of this planet to reach it, and it is still going. Every single second, the spacecraft moves another 10.5 miles farther from the Sun. It does not slow down. There is nothing out there to slow it down. No air, no friction, no resistance of any kind. Just vacuum, silence, and distance that grows without end. By the time you finish listening to this sentence, Voyager 1 will be roughly 50 miles farther away than it was when you started. By the end of this hour, it will have added another 38,000 miles to the gap. By tomorrow, it will be nearly 1 million miles farther from home than it is right now. The distance is not a number. It is a process. It is happening continuously, and it never pauses. Most people, when they hear about Voyager 1, think of it as a distance record, the thing that went the farthest. A trophy in a case. But that framing misses the part of the story that actually matters. Because the real question about Voyager 1 was never how far it could go. It was always how long it could keep talking to us while it did. To understand why that distinction changes everything, you need to go back to the beginning. Not all the way to the Big Bang. Just to a room full of engineers in Pasadena, California, in the early 1970s, who were handed a problem that comes around once every 176 years. The outer planets of our solar system, Jupiter, Saturn, Uranus, and Neptune, spend most of their time scattered across different regions of their orbits. They are so far apart and move so slowly that aligning them in any useful configuration for a spacecraft flyby takes nearly 2 centuries. But in the late 1970s, a rare geometric window was opening. The 4 giant planets would be arranged in a loose arc on the same side of the Sun, close enough in alignment that a single spacecraft, if launched at precisely the right moment, could use the gravity of each planet to slingshot itself toward the next. One shot, 4 planets. A grand tour that nature would not offer again until the 22nd century. NASA's Jet Propulsion Laboratory designed 2 spacecraft for the job. They were identical twins, built from the same blueprints, carrying the same instruments, wrapped in the same gold-colored thermal blankets. The total cost of both missions, including launch vehicles, operations, and the nuclear power sources provided by the Department of Energy, came to roughly $865 million. That was a bargain for what it delivered. No single spacecraft, before or since, has returned more raw scientific discovery per dollar than the Voyagers. The gravity assist concept is what made the whole thing possible. When a spacecraft flies close to a planet on the correct approach angle, the planet's gravity accelerates the spacecraft and bends its trajectory, effectively slingshotting it toward the next destination without burning any fuel. The energy comes from the planet's own orbital motion. The planet slows down by an infinitesimal amount, so small it could never be measured, and the spacecraft gains speed. It is the closest thing to a free ride that orbital mechanics allows. And the alignment of the outer planets in the late 1970s offered the most efficient version of that ride that any living human would ever see. Voyager 2 launched first, on August 20th, 1977. Voyager 1 followed 16 days later, on September 5th. The launch itself nearly ended the mission before it began. During ascent, the Titan rocket's second stage shut down prematurely, leaving roughly 1,200 pounds of propellant unburned. The onboard computers of the Centaur upper stage recognized the shortfall and extended their own burn to compensate. The Centaur stage came within 3.4 seconds of exhausting its fuel before delivering Voyager 1 to the correct trajectory, 3.5 seconds. That is how close the farthest human journey ever taken came to failing on the launch pad. Despite leaving second, Voyager 1 was placed on a faster trajectory, one that would carry it to Jupiter and Saturn more quickly, but sacrifice any chance of visiting Uranus or Neptune. Its path was designed to take it close to Titan, Saturn's largest moon, whose thick atmosphere scientists were desperate to study. That flyby would bend Voyager 1's trajectory upward, out of the plane where the planets orbit, and send it climbing northward into open space with no further planetary targets ahead. It was, in a sense, a one-way ticket from the very beginning. The spacecraft itself is modest by modern standards. The central body is a 10-sided aluminum frame, roughly the size of a compact car. Attached to it is a 3.7-meter dish antenna, the high-gain antenna that points toward Earth and serves as Voyager's only meaningful link to home. Extending outward from the body on booms and struts are the science instruments, magnetometers, plasma detectors, cosmic ray telescopes, cameras, and spectrometers. Trailing behind on a separate boom are 3 cylindrical objects that look like industrial canisters. These are the radioisotope thermoelectric generators, the RTGs, and they are the reason Voyager 1 is still alive. The RTGs do not use solar panels. They cannot. At Saturn's distance from the Sun, sunlight is roughly 1% as intense as it is on Earth. By the time you reach interstellar space, the Sun is just another star in the sky, bright but not useful for power. Instead, the RTGs generate electricity from heat, specifically from the radioactive decay of plutonium-238. Each RTG contains 24 pressed spheres of plutonium dioxide. As the plutonium atoms decay, they release heat. Thermocouples inside the generators convert that heat into electricity through the Seebeck effect, the same principle that allows a temperature difference across 2 joined metals to produce a voltage. At launch, the 3 RTGs together produced roughly 470 watts of electrical power. That is less than a typical household hairdryer. It was enough, in 1977, to run every instrument on board, power the computers, heat the fuel lines, and drive the radio transmitter. But here is the critical detail that determines everything about Voyager 1's future. Plutonium-238 has a half-life of 87.7 years. That means every 87.7 years, half of the remaining plutonium has decayed into other elements that produce no useful heat. The process is relentless and perfectly predictable. You cannot stop it, you cannot slow it down, you cannot refuel the spacecraft. The power output drops by about 4 watts every single year, and it has been dropping since the moment the generators were loaded with fuel. By now, nearly 5 decades after launch, the RTGs are producing roughly half of their original output. The spacecraft that once ran comfortably on 470 watts is now surviving on something closer to 220. And 220 watts is not enough to run everything. It is not even close. The onboard computers alone consume a fixed amount. The transmitter draws its share. The heaters that keep critical systems from freezing require their own allocation. And then there are the science instruments, each one demanding a slice of a shrinking pie. When the pie gets small enough, the only option is to stop feeding some of the guests. That single fact, the slow bleed of 4 watts per year, is the clock that governs every remaining decision about Voyager 1's mission. Not the distance, not the signal delay, not the hazards of interstellar space, the power. The quiet, irreversible loss of 4 watts every year is what will eventually kill the mission. Not with a bang, not with a dramatic failure. With a series of impossible choices made by a small team of engineers in a building in Southern California who have to decide, year after year, which part of the spacecraft to sacrifice so the rest can keep functioning a little longer. Suzanne Dodd, the Voyager project manager at JPL, described the situation in plain terms. If they do not turn off an instrument now, the spacecraft would have only a few more months of power before they would need to declare the end of mission. That is not a hypothetical. That is a statement made in 2025 about a spacecraft that is still operating right now. But before the shutdowns began, before the triage and the hard calls, Voyager 1 did something extraordinary. It completed one of the most successful exploration campaigns in the history of science. At Jupiter, in March of 1979, Voyager 1 discovered that the moon Io was covered in active volcanoes, the first confirmed volcanic activity ever observed on another world. It mapped the intricate structure of Jupiter's atmosphere, revealing storm systems and wind patterns at a level of detail no telescope on Earth could match. It studied the faint ring system around Jupiter, detected intense radiation belts, and sent back images of the Galilean moons that transformed them from points of light into real, complex worlds. At Saturn, in November of 1980, the spacecraft examined the planet's ring system with a precision that rewrote every textbook on planetary science. It found that the rings, which through telescopes appeared as smooth, solid bands, were composed of thousands of individual ringlets, gaps, and structures shaped by gravitational interactions with Saturn's moons. It measured Saturn's atmosphere and discovered that the planet radiates more heat than it receives from the Sun. And then it turned its attention to Titan. The Titan flyby was the reason Voyager 1's trajectory had been shaped the way it was. Scientists knew Titan had a dense atmosphere, the only moon in the solar system with one, but they did not know what it was made of or what conditions existed beneath the opaque orange haze. Voyager 1 passed within 4,000 kilometers of Titan's surface and confirmed that the atmosphere was primarily nitrogen, with significant amounts of methane and other organic compounds. The surface pressure was roughly 1.5 times that of Earth. The temperature was brutally cold, around -179 degrees Celsius, but the chemistry hinted at something remarkable. Titan had conditions that, in some ways, resembled those of early Earth before life began. That single flyby opened a scientific door that would eventually lead to the Cassini-Huygens mission decades later. After Saturn, Voyager 1 had no more planets to visit. Its trajectory carried it upward and outward, away from the ecliptic plane where the planets orbit, climbing into regions of the solar system that no spacecraft had ever explored. For years, it flew in silence, sending back data about the solar wind and magnetic fields, but making no headlines. The cameras were turned off in 1990 to save power and memory, but not before the spacecraft performed one last act that would become its most iconic. On February 14, 1990, at the suggestion of astronomer Carl Sagan, Voyager 1 turned its camera back toward the inner solar system and took a series of 60 photographs. Together, these images formed a mosaic, a family portrait of the solar system as seen from outside. One of those images captured Earth from a distance of roughly 6 billion kilometers. In the photograph, Earth appears as a pale blue speck, smaller than a single pixel, suspended in a beam of scattered sunlight. It occupies less than 12/100ths of a pixel. The entire planet, every ocean, every continent, every city, every person alive, reduced to a fraction of a dot in a photograph taken by a machine that was already farther from home than any human creation had ever been. Sagan later wrote about that image in terms that have echoed through the decades. He called it a pale blue dot, and the name stuck. The photograph did not contain new scientific data. It did not resolve any open questions in planetary science. What it did was something harder to measure. It showed every human being who looked at it exactly how small their world is when seen from the place where Voyager 1 was standing. After that portrait, Voyager 1 settled into its interstellar cruise. The cameras went dark. The scan platform that aimed at them was locked. The software that processed images was eventually deleted from the onboard computers and from the ground systems that supported it. Even the ground-based computers that could interpret the camera data no longer exist. If someone at NASA wanted to take another picture with Voyager 1 today, they could not. The capability has been physically and digitally dismantled. It is gone. And the computers that remain on board are relics of an era that modern technology has left so far behind it is almost comical. Voyager 1's onboard processors handle roughly 8,000 instructions per second. A modern smartphone processes more than 14 billion. The spacecraft's total digital memory is roughly 68 kilobytes, an amount so small that it could not hold a single photograph from the phone in your pocket. Yet these antique systems, designed before the first Apple computer went on sale, continue to operate in an environment more extreme and more remote than any computing hardware has ever endured. The simplicity that makes them primitive by modern standards is also what makes them resilient. Fewer components mean fewer things to break. And in interstellar space, with no repair crew and no spare parts, resilience is the only currency that matters. What remained in terms of science instruments were the tools designed to study fields and particles. The magnetometer, the plasma wave subsystem, the cosmic ray subsystem, the low-energy charged particle detector, and the plasma science instrument. These were the tools that would matter for the next phase of the mission. Because Voyager 1 was approaching a boundary that no human-made object had ever crossed. The sun does not simply sit in empty space radiating light. It also emits a continuous stream of charged particles called the solar wind, a flow of protons and electrons that races outward at hundreds of kilometers per second. This wind inflates a vast bubble around the sun called the heliosphere, a region where the sun's magnetic field and particle output dominate the local space environment. Beyond the heliosphere lies interstellar space, the medium between stars, filled with its own plasma, its own magnetic fields. and its own cosmic rays originating from sources scattered across the galaxy. The boundary between these two regions is called the heliopause. Scientists had theorized about it for decades, but no one had ever directly measured it. Models predicted where it should be, but models disagreed with each other, sometimes by billions of miles. The only way to know for certain was to send something through it and see what changed. The approach was not sudden. In 2004, Voyager 1 crossed an earlier boundary called the termination shock, the point where the solar wind abruptly decelerates from supersonic to subsonic speeds as it collides with the pressure of the interstellar medium. That crossing told scientists the heliosphere's outer edge was getting close, but close in this context still meant years of travel. The spacecraft spent 8 more years pushing through a turbulent region called the heliosheath, where the slowed solar wind piles up and churns against the incoming interstellar pressure. Then, in August of 2012, Voyager 1's instruments registered a dramatic shift. The density of solar wind particles plummeted. The intensity of galactic cosmic rays surged. The magnetic field changed character. The plasma wave instrument detected vibrations in the surrounding medium, consistent with the density of interstellar plasma rather than solar wind plasma. After months of analysis and a vigorous scientific debate about whether the crossing was complete or partial, NASA confirmed in September of 2013 that Voyager 1 had entered interstellar space. It had crossed the heliopause. It was officially outside the Sun's protective bubble. For the first time in the history of life on Earth, something built by human hands was touching the space between the stars. The crossing was not instantaneous. The heliopause turned out to be a complex, layered transition zone rather than a clean boundary. Voyager 1 passed through regions where solar particles were depleted, but the magnetic field had not yet rotated to match the interstellar direction. Scientists described it as a cosmic shoreline, where the waves of 2 different oceans met and mixed before one gave way to the other. The data Voyager 1 returned from this crossing was scientifically priceless. No model had predicted the exact structure of the boundary. No simulation had captured the precise way the solar wind gives way to interstellar plasma. Every measurement was new. Every data point was the first of its kind. And it came from an instrument suite designed in the early 1970s, built with technology that predates the personal computer, running on a power source that was slowly, irreversibly fading. That last detail is the one that changes the story, because crossing into interstellar space was not the end of Voyager 1's journey. It was not even the climax. It was the moment when the real question became unavoidable. The spacecraft had reached a place where the science was unlike anything available from any other source. The data it was sending back could not be replicated by any telescope, any simulation, any other mission in existence or in planning. No other spacecraft has entered interstellar space with a functioning instrument suite. Voyager 2 crossed the heliopause in 2018, but on a different trajectory and with a different set of operational instruments. Together, the 2 probes provide the only direct measurements humanity has of the environment between the stars. Every reading from Voyager 1's magnetometer, every detection from its plasma wave subsystem is the first and only measurement of its kind from that specific point in interstellar space. There is no backup. There is no replacement mission. When the instruments go dark, the data stream ends permanently. And the power keeping it alive was draining away at a rate of 4 watts per year. Voyager 1's radio transmitter operates at 23 watts. To put that in perspective, a refrigerator light bulb uses about 40. A standard household lamp uses 60. Voyager 1 whispers to Earth with less power than the light you leave on beside your bed. And yet, that whisper crosses more than 15 billion miles of vacuum and arrives at the Deep Space Network's massive dish antennas, with a signal so faint that the power received on the ground is 20 billion times weaker than what it takes to run a digital watch. The fact that we can hear it at all is a testament to engineering precision that borders on the absurd. The spacecraft's 3.7-meter dish antenna focuses the signal into a narrow beam aimed directly at Earth. On the ground, NASA's Deep Space Network uses antennas up to 70 meters in diameter to collect every photon of that signal. The largest of these, Deep Space Station 43 in Canberra, Australia, is the only antenna on Earth with enough sensitivity to both send commands to and receive data from the Voyager probes. It is a single point of contact. If that antenna goes offline, which it did for upgrades beginning in May of 2025, the ability to command the Voyagers is temporarily lost. The communication link is real. It works. It is one of the most extraordinary feats of long-distance communication ever achieved. But it exists on a margin so thin that the engineers who maintain it describe the spacecraft's status with a phrase that should make you pause. They call everything on board a single string. That means there are no backups. Every system, every thruster, every heater, every instrument is the last one. If any critical component fails, there is nothing to switch to. The mission continues, whatever still works, or it does not continue at all. And here is the part that most people do not think about when they imagine Voyager 1 sailing through the stars. The spacecraft does not just need power to run its instruments, it needs power to keep itself warm. Space is cold. The temperature of the interstellar medium is only a few degrees above absolute zero. Voyager 1's fuel lines carry hydrazine, a propellant used by small thrusters to keep the antenna pointed at Earth. If those fuel lines freeze, the thrusters stop working. If the thrusters stop working, the antenna drifts off target. And if the antenna drifts off target, the signal is lost, not weakened, lost. The beam is so narrow, and the distance is so great, that even a small misalignment means the whisper misses Earth entirely. Heaters that once kept those fuel lines warm have already been turned off to save power. The spacecraft is operating at temperatures it was never designed to endure. Components that were tested to function at certain minimum temperatures are now operating below those thresholds, surviving on thermal inertia and engineering margins that the original designers built in but never expected to need. The engineering team does not know exactly when a fuel line will freeze. They only know that each year, as power drops by another 4 watts, the thermal margin shrinks. The spacecraft gets a little colder, the risk gets a little higher. And the window between functioning mission and permanent silence gets a little narrower. There is a brutal asymmetry in this situation. If a fuel line freezes and the thrusters fail and the antenna drifts off target, the mission is over instantly. There is no recovery. There is no second chance. The spacecraft would still exist, still move, still carry the golden record and the instruments and every piece of hardware that launched in 1977. But it would be pointed at nothing, speaking to no one. A machine still traveling at 38,000 miles per hour, still crossing interstellar space, still technically operational in every other respect, permanently deaf and permanently mute because one tube of hydrazine got too cold. This is the reality that the distance numbers do not capture. Voyager 1 is not just far away, it is dying. Slowly, predictably, 1 watt at a time, and the distance it can still travel is essentially infinite. There is nothing in its path to stop it. No wall, no barrier, no edge of space. It will continue moving at roughly 38,000 miles per hour for millions of years, long after every instrument has shut down, long after the transmitter has gone silent, long after the last watt of electrical power has faded and the plutonium has decayed into a lump of inert metal. The spacecraft will outlast its voice by an almost incomprehensible margin. The object will endure. The mission will not. That is the distinction this story is really about. Not how far Voyager 1 can go. It can go, essentially, forever. The question is, how long can it remain something more than a dark, silent object drifting through the void? How long can it remain a spacecraft, a voice, a connection between here and there? How long can the farthest thing humanity has ever made keep sending home the only measurements in existence from the space between the stars? The answer to that question is not found in the distance. It is found in the power curve, and the power curve has a shape that every engineer at JPL knows by heart. It goes down. It only goes down. And at the bottom of that curve, there is silence. That story continues inside that curve, in the rooms where engineers are making the hardest decisions of the mission, choosing which instruments to kill so the rest can survive, rationing the last watts of a power supply that has been declining since before most of them were born. What is happening right now, in real time, is a controlled dismantling of one of the greatest scientific instruments ever launched. And every shutdown brings the silence closer. When Voyager 1 launched in 1977, it carried 10 functioning science instruments. Each one was a specialized tool designed to study a different aspect of the planets and space environments it would encounter. There were cameras for visible light, a pair of them, one wide angle and one narrow angle, mounted on a scan platform that could be aimed at targets as the spacecraft flew past. An infrared spectrometer measured heat signatures, mapping temperature variations across planetary surfaces and atmospheres with a precision that ground-based telescopes could not match. An ultraviolet spectrometer studied atmospheric chemistry by analyzing how planets absorbed and emitted light at ultraviolet wavelengths, revealing the composition of gases that were invisible to cameras. A photopolarimeter analyzed how light scattered off surfaces and through atmospheres, providing information about particle sizes in planetary rings and cloud layers. A planetary radio astronomy receiver listened for natural radio emissions from Jupiter and Saturn, signals generated by the planet's magnetic fields and charged particle environments. And then there were the fields and particles instruments, the 5 tools designed to study the invisible environment of space itself: the magnetometer, the plasma science instrument, the plasma wave subsystem, the low-energy charged particle detector, and the cosmic ray subsystem. Together, they made Voyager one of the most comprehensively equipped scientific platforms ever launched. 10 instruments, 11 separate scientific investigations designed by teams at universities and laboratories across the country, all riding on a spacecraft powered by less electricity than a kitchen appliance. As of today, 3 of those instruments still function. 3 out of 10. The other 7 are gone. Some were switched off decades ago when the planetary encounters ended and their measurements were no longer relevant to the Interstellar mission. The cameras went dark in 1990. The infrared spectrometer stopped operating in 1998. The ultraviolet spectrometer held on for years, enduring temperatures far below its design limit, before eventually being shut down. The photopolarimeter and the planetary radio astronomy receiver were deactivated after the Saturn flyby, their purpose fulfilled. The plasma science instrument on Voyager 1 stopped working properly in 1980 and was formally turned off in 2007. Each shutdown represented a small funeral, a capability that would never return. A sense that the spacecraft was shedding its skin, piece by piece, becoming simpler and more fragile with every instrument that went dark. But the shutdowns that happened in the early decades were relatively painless. They involved instruments whose scientific purpose had expired. Turning off the cameras after the pale blue dot portrait was emotional, but it was not a sacrifice. The cameras had nothing left to photograph. The real agony began when the power decline started eating into the instruments that were still doing irreplaceable science. To understand what it feels like inside the Voyager operations room during one of these decisions, you need to appreciate the scale of what is being lost. The fields and particles instruments are the reason Voyager 1 still matters scientifically. They are measuring things that no other instrument in existence can measure. The magnetometer detects the direction and strength of magnetic fields in interstellar space, data that tells scientists how the galaxy's magnetic environment is structured at scales that cannot be observed from Earth. The plasma wave subsystem listens for vibrations in the plasma surrounding the spacecraft, oscillations that reveal the density of the interstellar medium and detect disturbances propagating outward from the Sun. The cosmic rays subsystem counted high-energy particles streaming in from across the galaxy, measurements that help scientists understand the energy environment between stars. The low-energy charged particle detector tracked ions and electrons in the surrounding space, mapping the behavior of matter in a region no instrument has ever sampled before. Every one of these instruments produces data that exists nowhere else. There is no telescope that can replicate what a magnetometer measures from inside interstellar space. There is no simulation that can substitute for a direct plasma density reading taken 15 billion miles from the Sun. When one of these instruments goes dark, the data it collected is the last data of its kind that humanity will have for decades, possibly generations, until another probe is sent to follow the same path. And right now, no such probe exists even on a drawing board. That is the context in which the engineering team at JPL makes its decisions. They are not choosing between good options. They are choosing between terrible ones. Keep this instrument alive and risk overdrawing the power supply, which could trigger the spacecraft's fault protection system and potentially end the entire mission in an instant. Or shut the instrument down, preserve the power margin, and accept that a stream of irreplaceable scientific data has stopped forever. The process accelerated sharply in the early 2020s. For years before that, the team had been turning off heaters, one by one, to free up watts for the science instruments. Each heater shutdown was its own gamble, a calculated risk taken in the dark. The instruments mounted on the long 43-foot fiberglass boom extending from the spacecraft body depend on heaters to keep their components above the minimum operating temperature. Without those heaters, the instruments are exposed directly to the thermal environment of interstellar space, where ambient temperatures hover just a few degrees above absolute zero. When a heater goes off, the instrument it was protecting drops in temperature by tens of degrees, sometimes crashing through its tested operating floor within days. Linda Spilker, the Voyager project scientist, described one of these moments with a mixture of astonishment and relief. "They turned off the heater for the cosmic ray detector," she said, "and the temperature plummeted by 60 or 70 degrees Celsius, well outside any tested operating limits. Everyone expected the instrument to die. It did not. It kept working." Instruments, designed in the 1970s, tested in laboratories that no longer exist, built with materials whose behavior at these temperatures was never characterized, continued to function in conditions that would have been considered impossible during the design phase. That resilience bought time, but it did not buy a solution. The power curve kept falling. 4 watts per year, every year, with no exceptions and no reversals. By 2024, the team had squeezed every possible watt out of the non-science systems. They had adjusted how the spacecraft's voltage was monitored, recalibrating the safety margins to allow the power supply to operate closer to its limits. They had turned off every heater they could justify turning off. They had shut down every engineering subsystem that was not absolutely critical to keeping the spacecraft pointed at Earth and the transmitter running. There was nothing left to sacrifice except the science instruments themselves. On February 25, 2025, they turned off the cosmic ray subsystem on Voyager 1. The instrument that had helped determine the exact moment the spacecraft crossed into interstellar space in 2012, the instrument that had been counting galactic cosmic rays for nearly half a century, went silent. Its 3 telescopes, which had measured the energy and flux of protons streaming in from sources scattered across the Milky Way, stopped collecting data. The last reading that was ever taken joined the archive. Nothing will follow it. 3 instruments remained on Voyager 1 after that shutdown. The magnetometer, the plasma wave subsystem, and the low-energy charged particle detector. But the power curve does not stop, and the plan was already in place for the next step. The low-energy charged particle instrument is scheduled to be shut off in 2026. After that, only 2 instruments will remain. The magnetometer and the plasma wave subsystem, both housed inside the body of the spacecraft, where residual heat from the onboard computers keeps them barely warm enough to function. Those 2 instruments are expected to be the last ones standing. Engineers believe the spacecraft could continue operating with at least one of them into the early 2030s. Maybe. If nothing else, breaks first. And things do break. That is the part of the story that turns the slow decline into something more urgent, more frightening. Because Voyager 1 is not just losing power. It is falling apart. On November 14, 2023, Voyager 1 stopped making sense. The spacecraft was still receiving commands from Earth. The radio link was intact. The signal strength was normal, but the data coming back was gibberish. Instead of the organized packets of science and engineering information that the ground team expected, Voyager 1 began transmitting a repeating pattern of ones and zeros that carried no meaning. It was as if the spacecraft could still speak, but had forgotten every word it knew. The voice was there. The language was gone. The problem was traced to the Flight Data Subsystem, the FDS, one of 3 onboard computers. The FDS is the machine responsible for gathering readings from every science instrument and every engineering sensor on board, packaging them into a single, organized data stream, and passing that stream to the radio transmitter for broadcast to Earth. Without the FDS functioning correctly, Voyager 1 could collect all the data in the universe and never deliver a single useful bit of it home. The diagnosis took months. Every command sent from Earth required 22.5 hours to reach the spacecraft. Every response took another 22.5 hours to return. A single exchange, 1 question and 1 answer, consumed nearly 2 full days. And the team could not simply reboot the computer. Voyager 1's systems are not like modern machines with operating systems designed to restart cleanly. These are custom-built processors from the 1970s, running assembly language code on hardware that was manufactured before the first commercial microprocessor became widely available. A forced restart carried the risk of making things worse, potentially much worse, and at a distance where any mistake would take 2 days to even discover. In March of 2024, the team sent what they called a poke, a diagnostic command designed to prompt the FDS to dump its entire memory contents back to Earth. The full readout arrived after the usual 2-day round trip. An engineer at the Deep Space Network decoded it and found the answer. A single memory chip inside the FDS had failed. The chip held roughly 3% of the computer's total memory, but that 3% contained lines of code essential for packaging data before transmission. Whether the failure was caused by a cosmic ray strike, a charged particle slamming into the silicon at high speed and flipping a bit permanently, or by simple material degradation after 46 years of continuous operation in deep space, nobody could say for certain. What they could say was that the chip was dead and could never be repaired. The fix required a kind of remote surgery that borders on the miraculous. The team needed to relocate the corrupted code to other parts of the FDS memory. But the computer's total memory is roughly 68 kilobytes. There was no single open block large enough to hold the affected code in one piece, so they broke the code into fragments. They identified unused corners of memory scattered across the system. They deleted routines the spacecraft no longer needed, including software from the 1979 Jupiter flyby that had been sitting in memory for 45 years, doing nothing to clear room. They rewrote the fragments to ensure they would still function as a coherent whole, even when stored in separate locations. They updated every reference in the rest of the system that pointed to the old memory address. And then they transmitted the patch, knowing it would take 22.5 hours to arrive and another 22.5 hours before they would know whether it worked or whether they had just made things worse. On April 18th, 2024, they sent the first batch of relocated code. On April 20th, engineering data came through clearly for the first time in 5 months. The team at JPL gathered in a conference room and watched the signal resolve on their screens. 5 months of uncertainty, 5 months of not knowing whether the farthest human-made object had permanently lost its ability to speak, ended in a single moment when the data stream snapped back into coherence. By June, all 4 remaining science instruments were transmitting again. The spacecraft was back. 5 months of silence, 1 failed chip, and an act of digital archaeology performed across 15 billion miles of vacuum using assembly language, 16-bit words, and a computer architecture so old that the engineers who designed it have long since retired. One propulsion engineer on the team described the ongoing work of keeping Voyager alive in 2 words: palliative care. The phrase carries a clinical precision that cuts through the romance of space exploration. This is not discovery anymore. This is end-of-life management for a machine that has outlived its warranty by a factor of 10. But the crisis was not over. It was merely paused. In October of 2024, Voyager 1 went dark again. The mission team had sent a routine command to turn on one of the spacecraft's heaters. It should have been a simple operation. The spacecraft had enough power. The command was correctly formatted. But something unexpected happened. The fault protection system, the automatic safety program hardwired into Voyager 1's logic, interpreted the heater activation as a power threat. It triggered. And when it triggered, it shut down the primary X-band radio transmitter. This was the transmitter Voyager 1 had used to communicate with Earth for over 4 decades. Without it, the spacecraft automatically switched to its backup, a weaker S-band transmitter that had not been used since 1981. 43 years dormant. No one knew whether it still worked. The S-band signal operates at a different frequency and is significantly fainter than the X-band. At Voyager 1's distance, where the primary transmitter's signal already arrives as one of the faintest artificial signals ever detected on Earth, a further reduction in signal strength was potentially catastrophic. It was not clear whether Earth's antennas could even detect it. Engineers at the Deep Space Network searched for the weaker signal and found it, barely, like hearing a whisper from the far end of a stadium. They were able to confirm that the spacecraft was otherwise stable and to begin working on restoring the X-band transmitter. By mid-November, the primary transmitter was back online and data collection resumed from all 4 science instruments. The entire incident, from trigger to recovery, had unfolded across weeks, each step requiring that agonizing 2-day communication cycle. But the incident exposed a deeper problem. The fault protection system's models of how much power each subsystem consumes are estimates. They were built decades ago and have been updated over the years, but they carry uncertainty. Components age. Their power consumption changes in ways that cannot be perfectly predicted from 15 billion miles away. The fault protection system is designed to be conservative, to shut things down rather than risk an overload. And in a spacecraft where every remaining system is essential, a conservative shutdown can take out something critical. The team recalibrated the voltage monitoring method on both Voyager probes after the incident, adjusting the thresholds to reduce the chance of a false trigger. But they cannot eliminate the risk entirely. The fault protection system is not optional. Without it, a genuine power overload could damage the spacecraft beyond recovery. The choice is between a system that might shut things down unnecessarily and no safety net at all. Neither option is comfortable when you are managing the most distant functioning machine in human history. And then there is the antenna. The 70-meter dish at Deep Space Station 43 in Canberra, Australia, is the only antenna on Earth capable of sending commands to the Voyager spacecraft. Other antennas in the Deep Space Network can receive the faint Voyager signal, but Canberra is the only station with enough transmit power to reach the probes at their current distance. It is a single point of failure, not on the spacecraft, but on the ground. If that antenna goes offline, mission controllers can still listen, but they cannot speak. In May of 2025, Deep Space Station 43 went offline for major upgrades. The work is scheduled to continue until February of 2026, with only limited operational windows in August and December of 2025 for essential commanding. The upgrades are necessary. The antenna is aging, and the improvements will increase its capacity for future missions, including crewed lunar landings under the Artemis program and the growing demands of the Mars exploration fleet. The Deep Space Network as a whole is under extraordinary strain, supporting over 40 active missions with a finite number of antennas. A NASA Inspector General report noted that missions, including Voyager 2 and New Horizons, who had received between 8,500 and 15,000 fewer tracking hours than requested over a 5-year period. The network is oversubscribed, and the Voyagers, for all their historic significance, are not the highest priority in a system that must also support spacecraft carrying human crews. But during the months of Canberra's downtime, the Voyager team cannot send commands to either spacecraft. If something goes wrong, if a thruster fails, if a fault protection trigger shuts down the transmitter again, if a heater needs to be adjusted, the team can do nothing but watch and wait. The spacecraft are on their own, running on the last commands they received, surviving on the autonomy that was built into them nearly 50 years ago. Before the antenna went offline, the engineering team scrambled to prepare the spacecraft for the silence. In May of 2025, they successfully revived a set of backup roll thrusters on Voyager, one that had been dormant since 2004. The thrusters are used to keep the spacecraft pointed at the correct orientation so its antenna stays directed at Earth. The primary thrusters had been degrading due to clogging in their hydrazine fuel lines, a problem caused by silicon dioxide residue building up inside the narrow tubes over decades. Reviving the backups gave the spacecraft a fresh set of attitude control capability, buying time against the day when the primary thrusters fail permanently. The revival was performed just before the Canberra antenna went dark, a deliberate act of preparation for a period when no help could be sent. The hydrazine itself is finite. It is not renewable. The spacecraft launched with a measured quantity of fuel, and every thruster firing consumes a small amount. Unlike the power supply, which declines predictably, the fuel situation is harder to track precisely from Earth. The team estimates how much remains based on models of usage over the decades, but they cannot directly measure the tank level. They know the fuel is running low. They know that once it is gone, the thrusters stop. and when the thrusters stop, the antenna drifts. And when the antenna drifts, the mission ends. This is what the final years of Voyager 1 look like from the inside. Not a single dramatic failure, not an explosion or a collision or a sudden loss of signal. A slow, grinding negotiation between a machine that is running out of everything and a team of humans who are determined to keep it alive for as long as physically possible. Every decision is a trade-off. Every year brings fewer options. Every solution creates a new vulnerability. The timeline, as best as anyone can project it, looks something like this. The low-energy charged particle instrument will be shut off in 2026. That instrument measures ions and electrons in the interstellar medium, tracking the behavior of charged matter in a region of space that has never been directly sampled before. Its rotating platform, powered by a stepper motor that fires a pulse every 192 seconds, was originally tested to last 500,000 steps, enough to guarantee operation through the Saturn encounter. By the time it shuts down, it will have completed millions of steps, an endurance record that no one who tested it could have imagined. After that, approximately 1 year of operation with the remaining instruments before another shutdown becomes necessary. The magnetometer and the plasma wave subsystem are expected to be the final survivors, kept alive by their location inside the spacecraft body, where the computers provide residual warmth. They sit close to electronics that generate small amounts of waste heat as a byproduct of normal operation, a warmth that is incidental but essential, the difference between an instrument that functions and one that freezes. Science data collection could continue into the early 2030s, depending on how the power curve behaves and whether the instruments continue to function at temperatures they were never designed to endure. After the last science instrument goes dark, the spacecraft may still be able to transmit engineering telemetry, basic health data about its own systems for several more years. NASA estimates that Voyager 1 could remain within range of the Deep Space Network through approximately 2036. That date is not a wall. It is a horizon, the point beyond which the power supply will likely be too low to run the transmitter, or the signal too faint to detect, or the thrusters too depleted to keep the antenna pointed home. Some combination of these factors will converge, and the last bit of data will cross the 15 billion mile gap, and then there will be nothing. The people who will experience that moment are already working on the mission. Many of them have spent their entire careers with Voyager. Some joined as young engineers and are now approaching retirement. The Voyager team at JPL is small, far smaller than the teams that operate newer, higher-profile missions. They work in a building that has not been renovated in decades, using ground systems that have been adapted and patched over the years to keep up with a spacecraft that keeps outliving every prediction. Linda Spilker, the project scientist, has been involved with Voyager since the Saturn encounter in 1980. She has watched instruments shut down one by one across 4 decades. She has seen the team shrink as budgets tightened and newer missions claimed priority. And she has continued to advocate for every additional year of operation because she understands what no budget spreadsheet can capture. Every minute of every day, the Voyagers explore a region where no spacecraft has gone before, she has said. That also means every day could be our last. But that day could also bring another interstellar revelation. There is a weight in those words that goes beyond professional dedication. These are people who have spent their lives listening to a voice that is getting quieter. They know the silence is coming. They have calculated its approximate arrival, and they continue to show up every day, send their commands, wait for their 2-day round trips, and coax one more measurement out of a machine that, by every reasonable engineering standard, should have died decades ago. The spacecraft that launched with 10 instruments now operates 3. The power supply that began at 470 watts now hovers around half that. The fuel lines that were designed for a 4-year mission have been carrying hydrazine for nearly 50 years. The memory chip that packaged the data failed and was patched with a workaround that would have been considered impossible if anyone had proposed it during the design phase. The primary transmitter shut itself off and was brought back from a backup that had not been powered on in 43 years. The only antenna on Earth that can send commands went offline for upgrades, and the team prepared to revive thrusters that had been dormant for 21 years. Every one of those facts is an engineering story that deserves its own documentary. Together, they paint a picture of a mission that is not ending but narrowing, becoming thinner and more fragile, like a wire being drawn out until it is only a single strand. The strand has not broken yet. But it will. Not because of any failure of effort or ingenuity, because the physics will not negotiate. The plutonium decays. The power drops. The cold deepens. And at the far end of that process, on a day that no one will choose but everyone on the team has imagined, the last signal will arrive at the Deep Space Network, and after that, the dishes will point at the same patch of sky and hear only the background hiss of the cosmos. What happens after that moment is what we need to understand next, because Voyager 1 will not stop when the signal does. It will keep going, into a darkness that stretches further than any human mind has ever seriously tried to comprehend, and the distance it will cover in silence will dwarf everything it traveled while it could still speak. Sometime in the early 2030s, or perhaps a few years later if the engineering margins hold, the last instrument on Voyager 1 will go dark. The final measurement will be taken. The final data packet will be assembled by a computer running on the last trickle of electrical power from decaying plutonium, and the final transmission will leave the spacecraft's antenna at the speed of light, crossing 15 or 16 billion miles of vacuum before arriving at a dish antenna on Earth just over 23 hours later. Someone at the Jet Propulsion Laboratory will note the time. Someone will log the event. And then the Deep Space Network's antennas will continue to listen at the same frequency, pointed at the same patch of sky, and hear nothing but the faint hiss of the cosmic microwave background, the thermal afterglow of the universe itself. That will be the end of the mission. It will not be the end of Voyager 1. The distinction between those two sentences is the most important idea in this entire story. A mission is a relationship. It requires two ends of a connection, a sender and a receiver, a voice and an ear. When the power runs out and the transmitter falls silent, the relationship ends. The connection breaks. But the object that carried the connection continues to exist. It does not evaporate. It does not dissolve into the vacuum. It simply becomes something else. No longer a spacecraft in any operational sense, now an artifact, a relic. A piece of shaped metal and silicon moving through the galaxy under its own momentum, with no one listening and nothing to say. The spacecraft will still be there. It will still be moving. At the moment of its last transmission, it will be traveling at approximately 17 kilometers per second relative to the Sun, roughly 38,000 miles per hour. And here is the fact that transforms the story from an engineering narrative into something much larger and much stranger. Nothing will slow it down. There is no atmosphere in interstellar space. There is no friction. There is no drag. The density of matter between the stars is so low that Voyager 1 could travel for millions of years without encountering a single object large enough to affect its trajectory. The interstellar medium contains roughly 1 atom per cubic centimeter. For comparison, the air you are breathing right now contains roughly 25 quintillion molecules per cubic centimeter. Interstellar space is not merely empty. It is emptier than the best vacuum any laboratory on Earth has ever produced. In that emptiness, Newton's first law of motion operates in its purest form, as cleanly as it does in any physics textbook. An object in motion remains in motion unless acted upon by an external force. And the forces acting on Voyager 1 in interstellar space are so small that their effects accumulate over millennia rather than years. The gravitational pull of the Sun weakens with distance, but never quite reaches zero. At Voyager 1's current position, the Sun's gravity is still bending the spacecraft's path by a tiny amount, curving it ever so slightly. Over tens of thousands of years, the gravitational influence of nearby stars will begin to matter more than the Sun's. But none of these forces will stop the spacecraft. They will only adjust their course by fractions of a degree across timescales that make human history look like a single heartbeat. So Voyager 1 will keep going, not for decades, not for centuries, for a span of time so vast that it requires entirely new frames of reference to comprehend. The first milestone ahead is one that most people do not expect. Despite having crossed the heliopause and entered interstellar space in 2012, Voyager 1 has not yet left the solar system, not in the strict scientific sense. The solar system is defined not by the reach of the solar wind, but by the reach of the Sun's gravity. And the Sun's gravitational influence extends enormously farther than its particle output. The outermost gravitationally bound structure of the solar system is the Oort Cloud, a vast spherical shell of icy bodies that surrounds the Sun at distances ranging from roughly 1,000 to 100,000 astronomical units. 1 astronomical unit is the distance from the Earth to the Sun, about 93 million miles. The outer edge of the Oort Cloud lies at approximately 100,000 times that distance, roughly 1.5 light-years, nearly half the distance to the nearest neighboring star. No human has ever directly observed the Oort Cloud. No telescope has imaged it. Its existence is inferred from the orbits of long-period comets, ancient chunks of ice and rock that occasionally get nudged by the gravity of passing stars and fall inward on elongated orbits that carry them past the inner planets before swinging back out into the dark. The cloud is believed to contain roughly 100 billion comet-sized objects, remnants of the solar system's formation that were flung outward by the gravitational influence of the giant planets billions of years ago. Despite that staggering number, the volume of space the Oort Cloud occupies is so immense that each object is separated from its nearest neighbor by a distance comparable to the gap between the Earth and the Moon. Voyager 1, currently at roughly 172 astronomical units from the Sun, has not reached the Oort Cloud's inner edge. At its current speed, it will take approximately 300 years to get there. 300 years from now, long after the spacecraft has gone silent, long after the engineers who built it and the engineers who maintained it have all passed from living memory, Voyager 1 will arrive at the threshold of this immense cloud of frozen debris. And then comes the crossing. The Oort Cloud is not a wall or a belt. It is a shell, a three-dimensional region of space so enormous that Voyager 1 will spend roughly 30,000 years passing through it. 30,000 years. That is longer than recorded human civilization. 30,000 years ago, the last ice age was reshaping the continents. The earliest known cave paintings were created in Europe. Homo sapiens had not yet crossed from Asia into the Americas. The entirety of what we call human history, every empire, every discovery, every war, every work of art, has unfolded in less time than Voyager 1 will spend drifting through a single structure in its own solar system's backyard. The chance of Voyager 1 colliding with anything during this immense crossing is vanishingly small. The Oort Cloud contains perhaps 100 billion comet-sized objects, but the volume of space they occupy is so staggeringly large that the emptiness between them dwarfs anything the word cloud might suggest. One astronomer compared the probability of Voyager hitting an Oort Cloud object to the probability of winning a lottery, and then noted that the actual odds are 100,000 times smaller than even that. The spacecraft will pass through 30,000 years of cometary territory without coming close enough to any single object to notice it. After the Oort Cloud, the Sun's gravitational claim finally gives way. For the first time in its existence, Voyager 1 will feel the pull of other stars more strongly than the pull of the one it came from. It will be, by every meaningful definition, a free object in the galaxy. No longer tethered, no longer falling back, a piece of the solar system that the solar system can no longer recall. It will have taken roughly 30,000 years of silent travel to reach this point, a journey begun in the vacuum of interstellar space and completed in the vacuum of interstellar space, with no visible change in the environment, no signpost, no marker, just a slow mathematical transfer of gravitational allegiance from one star to the wider galaxy. If anyone were watching, they would see nothing happen. The transition is invisible, but it is real and it is permanent. The spacecraft that left Earth in 1977 will have finally, fully left home. In approximately 40,000 years, Voyager 1 will make its first close approach to another star. The word close requires heavy qualification. The star is Gliese 445, a red dwarf in the constellation Camelopardalis, currently about 17 light-years from Earth. Red dwarfs are the most common type of star in the Milky Way, small, cool, and long-lived, burning through their hydrogen fuel so slowly that they can persist for trillions of years. Gliese 445 is itself moving through the galaxy at a significant velocity, heading generally in the direction of our solar system. By the time Voyager 1 reaches its neighborhood, the star will have drifted considerably closer to the Sun's current position. The encounter distance will be roughly 1.6 light-years. For reference, the nearest star to the Sun right now, Proxima Centauri, is about 4.2 light-years away. So Voyager 1 will pass closer to Gliese 445 than Proxima Centauri currently sits to us. But 1.6 light-years is still an almost incomprehensible distance, roughly 9.4 trillion miles. If you could stand on Voyager 1 during the flyby, and if the spacecraft still had functioning cameras, which it will not, you would see Gliese 445 as nothing more than a dim red point of light, brighter than most stars in the sky, but not dramatically so. There would be no warmth, no illumination worth measuring, no meaningful gravitational interaction. The spacecraft would drift past, unaffected and unnoticed by both parties, and continue into the dark. If the star has planets, they would be far too distant to detect or influence the flyby in any way. The encounter would be a non-event physically. It would only matter to the species that launched the spacecraft, and by then, 40,000 years will have passed since that species last heard from it. It is worth pausing to consider what Voyager 1 will look like at that point. 40,000 years of exposure to the interstellar medium will have altered the spacecraft in subtle but real ways. The gold-plated thermal blankets that once gleamed under the cameras at Cape Canaveral will have been bombarded by interstellar dust grains, microscopic particles traveling at a few kilometers per second relative to the spacecraft. Each impact leaves a tiny crater in the surface, a vaporized pit smaller than a grain of sand. Over thousands of years, this bombardment produces a slow erosion, sandblasting the exterior surfaces at a rate determined by the density of dust in the regions the spacecraft passes through. Researchers at the Captain Astronomical Institute in the Netherlands have modeled this process in detail. They tracked the projected trajectory of both Voyager spacecraft forward through the galaxy's gravitational potential, simulating thousands of possible encounters with interstellar dust clouds over timescales stretching into the billions of years. Their findings offer a portrait of slow degradation rather than sudden destruction. After 5 billion years of travel, Voyager 1 has roughly a 99% chance of suffering damage that would render the exterior-facing side of the Golden Record unreadable. That sounds dire until you absorb the timescale. 5 billion years is longer than the current age of the Earth. It is roughly the remaining lifespan of the Sun before it exhausts its hydrogen fuel and expands into a red giant. Voyager 1's Golden Record may survive longer than the planet that created it. The Golden Record itself deserves attention here, because it is the part of Voyager 1 that was explicitly designed for this phase of the journey. The science instruments were built for the planetary encounters. The transmitter was built for the communication link. The RTGs were built for the active mission. But the Golden Record was built for the silence. It was designed for the moment when the spacecraft could no longer speak and had to carry its message in a form that did not require electricity, computation, or any active system at all. The record is a 12-inch disc of copper, plated first with nickel and then with a thin layer of gold. It sits inside a protective aluminum jacket mounted on the body of the spacecraft. Engraved into its surface are 115 images, encoded as audio signals, capturing everything from the structure of DNA to the skyline of a city to a photograph of a woman nursing her child. 90 minutes of music from cultures around the world are pressed into its grooves. Bach and Beethoven alongside Javanese gamelan and Navajo night chant, Chuck Berry's guitar alongside a shepherd's flute from Romania. Spoken greetings in 55 languages, ranging from ancient Akkadian, a tongue spoken in Sumer 6,000 years ago, to modern Mandarin, each one a few seconds long, each one a voice saying hello to a universe that may never answer. And woven among them is a collection of natural sounds: thunder rolling across a plain, wind moving through grass, birdsong in a forest, the calls of humpback whales echoing through the deep ocean, and the cry of a newborn child drawing its first breath. The cover of the aluminum jacket carries etched diagrams that explain, in the universal language of physics and mathematics, how to play the record, how to decode the images, and how to find Earth. A pulsar map identifies the Sun's position relative to 14 known pulsars using their precise rotation frequencies as coordinates. And electroplated onto the cover is a sample of ultra-pure uranium-238, whose half-life of 4.468 billion years provides a radioactive clock. Any civilization that finds the record can measure the ratio of remaining uranium to its decay products and calculate exactly how long the record has been traveling. The record was designed to last for at least 1 billion years. Its gold plating prevents chemical corrosion. Its copper substrate provides structural stability. In the near-total vacuum of interstellar space, there is no oxidation, no weather, no biological decay. The primary threat is the slow rain of micrometeoroid impacts and cosmic ray exposure, both of which degrade surfaces at rates measured in microns per million years. The grooves on the record, which encode all of its audio content, are measured in fractions of a millimeter. The margin between the depth of those grooves and the rate of erosion defines the record's useful lifespan. If Voyager 1 spends most of its journey in the relatively sparse regions between the Milky Way's major dust clouds, the record could remain at least partially readable for billions of years. There is a detail about the record's trajectory through the galaxy that the Dutch researchers highlighted and that most people have never considered. Voyager 1 does not travel in a straight line through the Milky Way. It orbits the galactic center, just as every star and every object in the galaxy does. but its orbit is not the same as the Sun's. The Saturn flyby in 1980 kicked Voyager 1 onto a trajectory that carries it upward out of the ecliptic plane, and that upward motion translates into a galactic orbit with a different inclination than the Sun's relatively flat path through the disk. Over millions of years, Voyager 1 will oscillate above and below the galactic plane, passing through the thicker dust concentrations near the midplane and then climbing into the sparser regions above and below it. Each pass through the midplane exposes the spacecraft and the record to higher erosion rates. Each excursion above or below the plane provides a relative respite. The researchers also noted that the gravitational influence of interstellar dust clouds, which can contain enormous amounts of mass concentrated in relatively small volumes, may occasionally bend Voyager 1's trajectory in significant ways. Over billions of years, these gravitational nudges could fling the spacecraft into substantially different orbits, sometimes pushing it farther from the galactic center, sometimes pulling it deeper toward the core. The long-term trajectory is not predictable with precision. It is chaotic in the mathematical sense, sensitive to conditions that cannot be measured in advance. But the spacecraft will survive. It will survive the Oort Cloud crossing. It will survive the stellar flyby. It will survive the slow erosion of its surfaces across millions of years. It will survive longer than most of the stars currently burning in the Milky Way. The aluminum, titanium, copper, and gold that compose its structure are stable elements. They do not decay radioactively. They do not break down in a vacuum. In the absence of a catastrophic collision, which the emptiness of interstellar space makes extraordinarily unlikely, the physical structure of Voyager 1 will persist for timescales that are difficult to distinguish from eternity. And here is the detail that pulls the entire story into sharp focus. All of that survival, all of those billions of years of endurance, will happen in total silence. The spacecraft will be carrying music it cannot play. It will be carrying greetings that it cannot speak. It will be carrying 115 images of Earth, its oceans, deserts, and cities and people, encoded in grooves that no human will ever hear decoded again. The transmitter will have been dead for billions of years. The computers will have been cold husks of silicon and copper for longer than the Sun has existed in its current form. The plutonium will have decayed through countless half-lives into a lump of lead and other stable isotopes, inert and lightless. And still the spacecraft will move. Still, it will cross the spaces between stars. Still, it will carry, on its side, a golden disk inscribed with the sound of a human heartbeat. There is one more milestone in Voyager 1's near-term future that bridges the gap between its active life and its silent eternity. In November of 2026, the spacecraft is projected to reach a distance of 1 light day from Earth. 1 light day. That means a signal traveling at the speed of light, the absolute maximum velocity permitted by the laws of physics, will require a full 24 hours to cross the gap between Voyager 1 and the planet that built it. A command sent on a Monday morning will not produce a response until Wednesday morning. The entire cycle of question and answer, a single exchange between humanity and its farthest creation, will consume 2 complete rotations of the Earth. The practical effect on mission operations is significant, though the team has been managing long delays for years and has built procedures to accommodate them. But the symbolic weight of the milestone is harder to dismiss. 1 light day is a clean, comprehensible unit of cosmic distance. It is not an abstract number of billions of miles. It is a measure of time translated into space. It places Voyager 1 at a point where the fastest thing in the universe needs an entire rotation of Earth to reach it. In November of 2026, Voyager 1 will likely still be operating, still sending data, still whispering from the edge of functionality. But the light day milestone will serve as a quiet announcement that the gap is becoming something more than distance. It is time. The space between Voyager 1 and Earth is no longer just far. It is a full day of the universe's speed limit wide. Beyond that, the trajectory stretches forward without any further human milestones for a very long time. In 300,000 years, Voyager 1 will pass within less than 1 light-year of a small star catalogued as TYC 3135-52-1. That encounter, like the Gliese 445 flyby, will be gravitationally insignificant. The spacecraft will not be captured. It will not be deflected in any meaningful way. It will simply pass through the outskirts of another star's gravitational domain and continue onward. After that, the timeline dissolves into galactic time. Voyager 1 will orbit the center of the Milky Way. It will complete one full galactic orbit in roughly 225 million years. It will make that orbit again and again, circling the supermassive black hole at the galaxy's core at a distance of tens of thousands of light-years, drifting through spiral arms and interarm regions, passing through dust clouds and emerging from them, accumulating damage on its outer surfaces, grain by grain, crater by crater, across a span of time that makes the age of the dinosaurs feel recent. In 5 billion years, the Sun will begin to die. It will swell into a red giant, consuming Mercury, Venus, and possibly Earth. The inner solar system will be sterilized. The Oort Cloud will be dispersed. Everything Voyager 1 left behind will be gone. The launch pad at Cape Canaveral will not exist. Florida will not exist. The Atlantic Ocean will have been boiled away. The planet, where 55 languages recorded their greetings onto a copper disk, will be a charred remnant orbiting inside the bloated atmosphere of its dying star. Or it will have been swallowed entirely, and Voyager 1 will still be out there, orbiting the galaxy, carrying the record, carrying the images, carrying the mathematics etched into its aluminum cover that explains how to find a star that no longer looks the way it did when the map was made. The pulsar map on the Golden Record's cover identifies the Sun by the frequencies of 14 pulsars, spinning neutron stars whose rotation rates were precisely measured in the 1970s. Over billions of years, those pulsars will slow. Their frequencies will shift. The map will become less accurate, then ambiguous, then unreadable. The coordinates will point to a star that has changed beyond recognition. The return address on humanity's message to the cosmos will eventually expire. NASA has said it plainly. The Voyagers are destined, perhaps eternally, to wander the Milky Way. The word eternally in that sentence is not poetic license. It is a reasonable approximation of the physics. Short of a direct collision with a large body, an event whose probability over any billion-year window is negligibly small, Voyager 1 will continue to exist as a physical object for as long as the galaxy itself persists. The Milky Way is expected to collide and merge with the Andromeda Galaxy in roughly 4.5 billion years. That merger will reshape the galactic structure, scatter stars into new orbits, and reorganize the gravitational landscape of the combined system over hundreds of millions of years. Voyager 1 will be swept along with whatever gravitational currents emerge from the collision. It will not be destroyed. The merger of two galaxies is not the violent crash that the word collision implies. The distances between individual stars are so vast that during a galactic merger, actual stellar collisions are extraordinarily rare. Stars and their orbiting debris pass through each other's systems like two swarms of insects flying through one another, each individual member separated by miles of empty air. Voyager 1 will simply find itself in a different galaxy, a merged one, carrying a record from a planet that orbited a star that no longer exists in a solar system that was absorbed into a larger cosmic structure billions of years before. The contrast is the point. The contrast is what makes this story unlike any other story in the history of exploration. The active mission, the part where Voyager 1 speaks and listens and sends and receives, occupies roughly 60 years out of a journey that will last for billions. The ratio of voice to silence is so extreme that it almost defies analogy. It is not a candle burning in a dark room. It is a single spark in a darkness that stretches from one end of time to the other. The spark was extraordinary. The data it produced rewrote textbooks. The images it captured changed how a species understood its own place in the universe. The instruments it carried measured things that had never been measured before and may not be measured again for generations. But the spark will go out, and when it does, the object that carried it will keep moving through a silence that has no boundary and no end, not falling, not decaying, not stopping, just drifting, endlessly, at 17 kilometers per second, through the space between the stars, carrying a golden record that plays the sound of surf and wind and a mother's first words to her child, in a language that will one day be as ancient and forgotten as the dust that slowly grinds the spacecraft's skin away. The rest of this story is about that moment, the moment the spark goes out. What it will look like from both ends of the signal. What does it mean for the people who will experience it? And why the most haunting thing about Voyager 1 is not that it stops moving. It stops answering. There is a room at the Jet Propulsion Laboratory in Pasadena, California, where a small team of engineers monitors the health of 2 spacecraft that are older than most of the people in the building. The room is not glamorous. It does not look like mission control in the movies. There are no rows of consoles with dramatic lighting, no giant screens showing real-time telemetry in glowing blue. There are desks, monitors, coffee cups, and printouts pinned to cubicle walls. The carpet is worn. The furniture has not been updated in years. The budget for the Voyager Interstellar mission is a fraction of what newer, more photogenic missions receive. The people who work here are not celebrities. Most of them have never been interviewed on television. They are not the faces on magazine covers or the subjects of Hollywood biopics. They come to work. They send commands into the void. They wait a day or two for an answer. And they make decisions that determine whether the farthest human-made objects in existence continue to function or fall permanently silent. The work is slow. The stakes are absolute. And the team gets smaller every year. Some of them have been doing this for decades. Linda Spilker has spent more than 4 decades listening for Voyager's voice and has outlasted every prediction about when that voice would stop. Suzanne Dodd has managed the project through years in which each new anomaly carried the real possibility of ending the mission entirely. Todd Barber, a propulsion engineer, once summed up his role in 2 words that no one on the team has forgotten. "The time that remains," he said, "still matters." That simple conviction is what keeps the operation going. These are the people who will be in the room when the last signal arrives, not the last dramatic signal. Not a distress call or a final burst of data marking some catastrophic event, just the last signal, the last packet of telemetry that the deep space network's antennas can pull out of the background noise. It might be a magnetometer reading, it might be an engineering health report, it might be a string of ones and zeros so faint that it takes hours of signal processing to confirm it is real. And after it arrives, there will be another scheduled contact window. The antennas will point at the same coordinates. The receivers will listen at the same frequency. And they will hear nothing. There will not be a moment of clarity. There will not be a clean ending. The signal will not cut off mid-sentence like a phone call dropping. What will happen is more like a voice fading at the far end of an enormous corridor, growing softer with each step the speaker takes, until the listener is no longer sure whether they are hearing a voice or imagining one. Each transmission will be a little weaker than the last. Each data packet will require a little more processing to decode. The engineers will push their equipment harder, refining their filters, extending their integration times, and combining the output of multiple antennas to extract one more coherent signal from the noise. At some point, the signal-to-noise ratio will drop below the threshold where the ground systems can distinguish Voyager 1's whisper from the ambient radio noise of the universe, the faint electromagnetic hum left over from the birth of the cosmos itself. The engineers will not be sure, at first, whether the silence is permanent. They will try again at the next window, and the next. They will adjust their receivers, widen their search parameters, and bring additional antennas into the array. They will do everything they can to hear one more word from a machine that has been talking to them for longer than many of them have been alive, and at some point, quietly, without ceremony, someone will update a log entry. Contact lost. The entry will include a date, a time, a set of coordinates marking the spacecraft's last known position, and a projected trajectory extending forward into a future that no human will ever verify. The Voyager Interstellar mission will be over. The longest-running space mission in history will have ended, not with a bang, not with a celebration, but with a room full of people listening to static and knowing that the voice they spent their careers preserving has finally dropped below the threshold of hearing. What makes that moment different from any other? End of mission event in the history of spaceflight is what comes after it. When the Cassini spacecraft ended its mission at Saturn in 2017, it was deliberately plunged into the planet's atmosphere. The spacecraft was destroyed. It burned up. It ceased to exist as a physical object. The mission ended because the vehicle was gone, entirely and irreversibly. There was grief in that ending, but there was also closure. The object and the mission ended together. When the Opportunity rover fell silent on Mars in 2018, buried under a global dust storm that starved its solar panels, the vehicle died in place. It is still there, sitting on the surface of Meridiani Planum, its wheels motionless, its cameras dark. But it is inert. Its journey is over. Its location is fixed. It will never move again. Someday, perhaps, a human expedition will find it, brush off the red dust, and bring it home to a museum. Its story has a resting place. Voyager 1 is different. When its mission ends, the spacecraft will not be destroyed. It will not be stationary. It will not be inert. It will continue moving at 38,000 miles per hour through interstellar space, fully intact, structurally sound, carrying every instrument, every antenna, every component it has carried since 1977. The only thing that will have changed is the silence. The spacecraft will be exactly what it was the day before, minus the ability to speak. And that distinction, the gap between an object that endures and a voice that fades, is what makes Voyager 1's ending unlike anything else in the history of human exploration. Every other great journey in history ended when the traveler stopped moving. The ships returned to port or sank to the bottom of the ocean. The expeditions reached their destination, turned back, or perished along the way. The astronauts splashed down in the ocean and were pulled from the water by recovery crews. Even the unmanned probes that ventured farthest either crashed, burned up, or came to rest on a distant surface. Voyager 1 will do none of those things. It will keep going. It will cross distances that make its entire active mission look like a prologue. And every mile of that crossing will happen in silence, with no one watching and no way to watch. There is a concept in philosophy called the ship of Theseus. It asks whether a ship that has had every one of its planks replaced one at a time, is still the same ship. Voyager 1 poses a different version of that question. Is a spacecraft that can no longer communicate still a spacecraft, or has it become something else? The hull is the same, the instruments are the same, the golden record is the same. But the thing that made it a mission, the connection to the people who launched it, is gone. Without that connection, Voyager 1 is no longer an extension of human curiosity reaching into the unknown. It is an object, a very special object, carrying a very special cargo, traveling at a very specific speed in a very specific direction. But an object nonetheless. The transformation from spacecraft to artifact will not happen because of damage or decay. It will happen because the relationship ended, because the conversation stopped, because one side of the dialogue ran out of power and the other side ran out of range, and the distance between them continued to grow at 10.5 miles every second, with no possibility of reversal. The engineers who manage the mission understand this transformation better than anyone. They talk about it in practical terms: power budget, instrument priorities, and signal margins. But underneath the engineering language, there is something else. There is the knowledge that they are the last people who will ever hear directly from the farthest thing humanity has ever made. After them, no one will. The data they collect in these final years is not just scientifically valuable, it is final. Every magnetometer reading is the last magnetometer reading that will ever come from that point in interstellar space. Every plasma wave detection is the last direct measurement of the interstellar medium from that trajectory. When the instruments go dark, those measurements stop, not temporarily, permanently. No future mission is planned to follow Voyager 1's path. No probe currently under development will reach the regions of space that Voyager 1 is crossing right now. The data stream that has been flowing from that spacecraft for nearly 50 years will simply end, and the region of the galaxy it was measuring will return to being unknown, a place that was briefly illuminated by a single set of instruments and then went dark again. There have been proposals for interstellar probes, concepts with names like the Interstellar Probe and the TAU mission, studies that imagine sending faster, more capable spacecraft to follow the Voyagers into the interstellar medium. None of them has been funded. None of them is under construction. None of them could launch in time to overlap with Voyager 1's remaining operational life. The earliest realistic timeline for a dedicated interstellar probe would place its launch decades from now, and even with advanced propulsion, it would take years or decades to reach the regions Voyager 1 is currently crossing. By then, the measurements Voyager 1 is making right now will be historical data, and the specific conditions at its specific location will have changed. What is being measured today will never be measured again, at least not in the same way, at the same place. At the same moment, in the evolution of the local interstellar medium. That is a loss that is difficult to articulate because it is not a loss of something tangible, it is a loss of presence. For nearly 5 decades, humanity has had a representative in interstellar space. A small, fragile, aging machine that carried human-built sensors into a place no human has ever been and reported back what it found. That presence is about to end. Not because we chose to end it. Not because we lost interest, because no amount of ingenuity can override thermodynamics. The fuel that powers the voice is finite, and it has been running down since the day it was loaded. And eventually the whisper drops below the threshold of hearing, and the representative goes silent, and the place it was speaking from becomes, once again, just another patch of emptiness between the stars. There is a particular cruelty in the way this ending unfolds. It is not sudden. It is not dramatic. It is not the clean, decisive ending of a mission that goes out in a blaze of atmospheric entry or a controlled impact. It is slow enough that everyone involved can see it coming and precise enough that they can calculate approximately when it will arrive. The engineers know roughly how many watts remain. They know roughly how many years each watt will buy. They know which instrument will be shut down next and which one will be last. They have a timeline, not exact, but close enough to feel the weight of each year as it passes. Close enough to count the remaining contact windows the way a patient counts remaining treatments. Each year is one step closer to the end of the conversation. Each shutdown is one fewer voice in the choir. And the people making those decisions carry the burden of knowing that every instrument they turn off is an instrument they will never turn on again. There is no reversal. There is no second chance. The shutdowns go in one direction, and the direction is towards silence. Consider what it means to send a command to a machine that is more than 15 billion miles away, knowing that by the time the command arrives, 23 hours will have passed. Knowing that by the time the response comes back, another 23 hours will have elapsed. Knowing that in those 46 hours, the spacecraft has moved another 1.7 million miles farther away, every exchange is conducted across a gap that is actively widening. Every conversation takes place between 2 points that are moving apart at a speed that nothing in the universe can reverse. The engineers are not just managing a spacecraft. They are maintaining a relationship across a distance that physics itself is conspiring to break. And yet, they continue. They continue because the data matters. They continue because no one else can do what Voyager 1 is doing. They continue because there is something in the human character that refuses to let go of a connection until the last possible moment, even when the outcome is certain, even when the silence is inevitable. Suzanne Dodd has said that if they did not keep fighting for every watt, the mission would have ended years ago. That duality, the acceptance of the ending and the refusal to stop trying, defines the closing years of this mission more than any technical specification ever could. When the silence finally comes, it will be permanent in a way that very few things in human experience are permanent. You cannot reboot a spacecraft that has run out of power 15 billion miles away. You cannot refuel a plutonium generator across an interstellar distance. You cannot send a repair crew to a vehicle that is receding at 17 kilometers per second with no way to slow down or turn around. The silence, when it arrives, is absolute. It is the end of a decades-long handshake, conducted at the speed of light across a gap that has been growing every single second since the day the spacecraft left Earth. One hand will simply stop squeezing, and the other will remain extended, still reaching, toward a point in the sky where something is still moving but can no longer be felt. The temptation, at the end of a story like this, is to reach for metaphors that soften the blow, to say that Voyager 1 lives on in spirit, that its legacy endures in the data it collected. The golden record carries humanity's voice forward even after the transmitter goes silent, and all of those things are true in their way. The data will survive in archives. The discoveries will persist in textbooks. The record will endure for billions of years, far longer than the civilization that made it. But none of those consolations change the central fact. The connection will be broken. The voice will stop. And the thing that made Voyager 1 extraordinary, the thing that separated it from every other piece of debris drifting through the cosmos, was never the hardware. It was the link. The living, active, two-way link between a machine in interstellar space and a room full of people in Pasadena who could still hear it. There is something in this story that goes beyond space exploration. It touches on a question that every person eventually faces. What does it mean to let go of something that is still there? Voyager 1 will not be gone when it goes silent. It will be right where it was the moment before, moving at the same speed, on the same heading, carrying the same cargo. The only thing that will change is our ability to reach it. And that change, the transition from presence to absence without the object itself changing at all, is one of the most quietly devastating concepts the human mind can encounter. The thing you are losing is not the thing that disappeared. It is the connection to the thing. The thing itself is fine. It is out there. It is intact. It is still going. You just cannot hear it anymore. That is why Voyager 1's story is not a story about distance. It was never really about how far it could go. Distance is just a number. Distance without connection is just emptiness with coordinates. What made the distance meaningful was the fact that across every mile of it, a signal was traveling. A whisper was crossing. A conversation was happening, however slow, however faint, however strained by the physics of light speed delay and decaying power supplies. The distance mattered because someone was on the other end of it. When that someone goes quiet, the distance does not change, but its character transforms entirely. It goes from being a bridge to being a wall, from being a challenge that human ingenuity is still meeting to being a fact that human ingenuity can no longer overcome. The distance that was once a testament to what we could reach across becomes a measure of what we have permanently lost, and Voyager 1 will not care. That is the part that is hardest to sit with. The spacecraft has no awareness. It has no sense of loss. It does not know that it once spoke and can no longer be heard. It does not know that it carries music from a planet it will never return to. It does not know that the record on its side contains greetings spoken in languages that may already be extinct by the time the spacecraft passes its first neighboring star. Voyager 1 is a machine. It does what the laws of physics dictate. It moves because nothing stops it. It carries the record because the record is bolted to its frame. It does not mourn the end of its mission because it was never aware that the mission existed. The mourning belongs to us. The meaning belongs to us. The loss, when it comes, belongs entirely to us. And that is what makes this ending so unusual in the history of exploration. We are not losing an explorer. We are losing the ability to hear from one. The explorer continues. The exploration does not. In a sense, Voyager 1's final silence will complete a transformation that began the moment it was launched. For the first 13 years of its journey, it was an active explorer, flying past worlds, photographing moons, discovering volcanoes, ring structures, and atmospheres that no one had ever seen. For the next several decades, it was a sentinel, monitoring the boundary between the solar wind and the interstellar medium, waiting for the crossing that came in 2012. For the years after that, it has been a pioneer, taking the first direct measurements of interstellar space, sampling an environment that exists nowhere else within human reach. And in its final phase, the phase that begins when the last instrument goes dark, it will become something else entirely. A monument. Not a monument built by intention, like a statue or a plaque erected in a public square. A monument created by physics and time. An object that exists in a place where nothing else humanity has made exists, carrying a message that no one may ever read, moving through a silence that will last longer than the species that launched it. It will join a category of objects that has no name, because no civilization has ever created one before. Human-made things that persist beyond the reach of human contact. Artifacts without an audience. Messages without a recipient. The only category that comes close is the deep-sea wreck, resting on an ocean floor where no one visits. But even wrecks have coordinates. Even wrecks can be found. Voyager 1, once it goes silent, will be unfindable. Its position will be known mathematically, projected forward from its last confirmed trajectory. But no instrument on Earth or in orbit will be able to detect it. It will be a known unknown, a thing whose existence is certain, but whose location is, for all practical purposes, lost. No space agency has ever published a more extraordinary sentence about any of its missions. The Voyagers will outlast their makers. That conclusion, stated without drama on an official government website, is not speculation. It concedes, without drama and without apology, that the thing we built will outlast us. Not might outlast us, will. The Voyager spacecraft will persist as physical objects in the galaxy for billions of years. They will orbit the galactic center long after the sun has died and the Earth has been consumed. They will carry their records through a future that contains no guarantees about the survival of the civilization that made them. And the records themselves, those golden discs with their greetings and their music and their encoded images of a blue and green world, will become something that no one intended. They will become the oldest surviving human artifacts. Older than any building, older than any city, older than any fossil of any creature that ever lived on Earth. The records were designed as messages. They will become relics. They were created as introductions. They will become epitaphs, not because they failed, but because the silence around them grew so vast that the distinction between a message and a memorial dissolved. The final image of this story is not complicated. It does not require special effects or dramatic music. It is simply this. Somewhere in the Milky Way, right now, at this exact moment, a small machine, no larger than a garden shed, is moving through absolute darkness at 17 kilometers per second. It is more than 15 billion miles from the nearest human being. Its power supply is fading. Its instruments are shutting down one by one. Its signal is growing weaker with every passing year. The people who keep it alive are working with margins so thin that a single frozen fuel line or a single failed chip could end everything in an instant. And yet, for now, it is still talking. For now, the antennas on Earth can still hear it. For now, the connection holds. But not for much longer. The power curve has a shape, and that shape only goes in one direction. The day is coming, visible on the timeline, calculable in watts and years, when the farthest thing humanity has ever built will send its last signal and receive no reply. The spacecraft will not stop. It will not break apart. It will not crash into anything. It will simply continue, carrying its golden record, carrying its greetings in 55 languages, carrying the sound of wind and whales and a newborn's cry, into a silence that has no end. And that is the answer to the question in the title: how far can Voyager 1 really go before it goes silent? The answer is not a number. It is not measured in miles or astronomical units or light years. The answer is that Voyager 1 can go forever. There is no limit to how far it can travel. The universe will not stop it. The galaxy will not slow it down. It will drift through interstellar space for billions of years, long after every trace of the civilization that built it has vanished from the surface of a planet that itself will one day cease to exist. But it will go silent, not because it reaches some barrier, not because space has an edge, because its power supply is finite, its transmitter needs electricity, and the plutonium that provides that electricity is decaying at a rate that no engineering decision can reverse. The silence is not imposed from outside, it comes from within. The spacecraft's own heart is slowing, beat by beat, watt by watt, year by year. And when the last beat fades, the spacecraft will still be there, still moving, still carrying everything we gave it to carry. It just will not be able to tell us about it anymore. That is the real frontier. Not the heliopause. Not the Oort Cloud. Not the space between the stars. The real frontier is the line between voice and silence, between a spacecraft and a relic, between a mission that is still speaking and an object that is only traveling. Voyager 1 will cross that frontier sometime in the next decade. And when it does, humanity's most distant creation will become its quietest. Still out there, still going, still carrying the sound of our world pressed into gold, answering to no one, heard nothing. Moving through the dark at the same speed it has maintained since a November afternoon in 1980, when Saturn's gravity bent its path upward and sent it climbing away from the plane of the planets, away from the warmth, away from the light, and into the longest silence any human object will ever know.